Okay, we derived the interval time for the Poisson process last time, and then we compute basically the mean and variance of the interval time for a Poisson process. So for this segment, I want to use the same picture that we used for deriving the interval time to find the distribution of how many packets that is going to be or will be arriving within a particular segment of time. So let's say we have a period of time here. Let's say I have this, just call it tau here. And I want to know, for this period of time tau, how many packets will that arrive. And of course, because the process itself is random, the best I can do is find a distribution. So I can also know deterministically how many packets will arrive. There will be 1, 2, or 3, and so on. But I want to know what is the probability that I have 3 packets or 4 packets arrive within this period delta tau. So again, what we are going to do is we are going to partition this period tau here into very tiny segment, tiny interval, and each of this interval with a width delta. So and let's say there will be n of them. So essentially tau is just equal to n delta. Now what we are going to do is just want to find the probability that, let's say, there will be n arrival, or maybe just m arrival will be easier, that I have one big n here already. So let's say what is the probability that I have m arrival within tau. So the probability will be basically that will be n segment here, right? Essentially, or n intervals here. Essentially, I need to this probability will be out of these n intervals, m of them have to have arrival, and the rest there will be no arrival. So therefore, this is just a combinatorial problem. So remember that the probability to have an arrival is just equal to lambda delta. And I have m of them has to have arrival, therefore it's lambda delta to the m. And I need to have the rest have no arrival, therefore I need to multiply this by 1 minus lambda delta to the power n minus m. And then because there will be many combinations of that that have essentially m arrival and m minus m no arrivals, because I can have the first m of them have arrival, or I can have the first one is actually no arrival and the next m of them has arrival. And this combinatorial problem will be just the number of this combination will be just n choose m, so it's actually just equal to n choose m, or NCM, or this NCM here is essentially just m factorial over m factorial m minus m factorial. One thing know that is we have n is actually much bigger than m, because we remember that delta is very small, n is essentially going to infinity, and what we're asking m here, m arrivals here, that will be just asking some finite number of arrivals. Typically, we will ask what's the probability to have 5, 10, or 100, even 200, but it's still a finite number. It's not like m that essentially can go infinite as we let delta to approach to take delta to goes to 0. So okay, let's just compute this expression here. and make some approximation. So I have n factorial over n minus n factorial, so essentially some of this term will get cancelled. What I get this here is actually just equal to n times n minus 1 up to n minus 1, n minus n plus 1. So that would be like, here I have m terms here. And as I already mentioned that as n is much bigger than m, therefore like n minus m plus 1 is essentially just equal to m. This is no different from is approximately equal to n. So I can approximate the whole thing is just like n to the m over m factorial. Okay, let's see what else we can do for the approximation here. We have let's see. Okay, that okay, remember that we have like tau is equal to n delta, so we can replace delta, or replace n with like tau over delta. Okay, let me replace n with, or maybe replace delta with tau over n. So let's say all of this delta becomes tau over n here, and this is 1 minus lambda tau over n minus m here. And now okay. Another thing is like, again, like n is much bigger than m. Actually, this number of terms here can be written as 1 minus lambda tau to the n times like 1 minus lambda tau to the n to the minus m, or like over 1 minus lambda tau to the n to the m. But because like n is very big, actually n will goes to infinity eventually. And this term here is actually, this is essentially just 1, and we multiply it in like 1 by m times, and this m is kind of finite, therefore this term is essentially just equal to 1 here. You can just write this, is actually just approximately equal to this. But the nice thing is that we know this expression here. If n goes to infinity, this expression here is just equal to e to the minus lambda tau. And let's see what else. And of course, like this get cancelled here. N to the m here and n to m here got cancelled. So therefore, we have lambda tau to the m here, m over m factorial here. And that's it. That's what we have here is the probability that have m arrivals within tau. And actually, one can easily check this is correct, because let me just write this like as denote this as P and M here, and this apparently we can have 0 arrivals, 1 arrival, 2 arrival, and so on. And all these probabilities, since they are probabilities, they have to sum up to 1. So therefore, we should have P and m sum over m equal to 0 to infinity is equal to 1. And we can verify that easily. E to the minus lambda tau, this is equal to, and I have lambda tau to the m over m factorial, m equal to 0 and infinity. And these parts have nothing to do with m, so let me just pull it out here. And this part, actually, this summation is exactly equal to e to the lambda tau. This is basically, I think it's the Euler equation. So this will just get cancelled, therefore it's just equal to 1. Okay. So anyway, that's what we derived this time, is basically the distribution of the number of packets arrived within a particular interval for a Poisson process. And actually, this distribution, this is of course a discrete distribution for a discrete random variable, is called the Poisson distribution. And I'm not sure which one is invented first, like whether it's Poisson distribution invented first or like the Poisson process is invented first. But anyway, this link really the connection somehow, like it helps you memorize why the Poisson process is known as Poisson process, because really the number of packets arrived within a particular period have a distribution is exactly the Poisson distribution. Okay, so we just show that like the probability of the number of packets arrive in a particular time tau, or period tau, is equal to, okay, let me write it down, number of arrival in tau, it will have that is equal to, if we have m arrival, let me denote that as a p n m, something like that, is equal to lambda tau to the m e to the minus lambda tau over m factorial. And we say that like this is a Poisson distribution, and we can again trying to find the mean and variance for the number of arrival within period tau. And to find that, we can again use the moment generation function, like in the case when we try to find the mean and variance for the interval time. But in this case, this distribution or the random variable here is discrete. So we have a moment generating function that instead of like essentially a Laplace transform of the distribution, it will be a Z transform of the distribution. So let's consider denote something like G Z, that is just the essentially the Z transform lambda tau to the m e minus lambda tau and factorial the Z transform of the distribution. So m equal to 0 to infinity, and then let's see, and then this will be just equal to lambda tau z m e minus lambda tau m factorial sum of s m equal to 0 to infinity. One thing I know is that this thing here, if I ignore this part here, this thing should be just sum over together, should be just equal to exponential minus lambda tau z, right? Or actually this part, when I sum together, should be just equal to exponential lambda tau z. Yeah. So therefore I multiplied by this, so I will just have lambda tau z minus 1. So that's it. It's a very kind of nice expression here. So again, like if we define this as the GC, if we look at here, if we take the derivative of GC with respect to z, then we will have m coming down there. So I will have something like taking m0 infinity. Let me just use p and m, c to the m here. If I take the derivative once, then with respect to c, then this will come down here, and this become m minus 1. Now if I set z equal to 1, then I will have this is essentially just equal to the mean, this expectation of this random variable here. I use n here, but okay, let's just use n here. And then similarly, I can just take the derivative twice, but unlike the case for continuous transform, I need to do something more, because if I take derivative twice immediately, I will have m minus 1 going down instead of m going down. If I want to find the second moment, that expectation n squared, then I better have something like going down at m instead. So what I'm going to do is I'm going to multiply by m first. So I will have GC, then have again m going down here, but I will multiply by the c first. So therefore this will become the c here. Then I take the derivative again. Then if I take the derivative again, then I will have m squared now. So it looks very nice again. If I just set c equal to 1, that will be just equal to the second moment here. So okay, just use this moment generation function to compute the mean and variance here. Then the mean will be just equal to taking this derivative once, I should have lambda tau going down here, an exponential. Now the tau c minus 1 here. I set c equal to 1, this just becomes 1, so it's just equal to lambda tau. It's quite reasonable. Like think of like lambda is the arrival rate, and tau we're looking at a period tau here, and we are asking on average how many packets will arrive in this period tau. Of course, this will be just lambda tau. And let's see how about this second moment here. For the second moment, I need to take derivative once. I get lambda tau e lambda tau c minus 1. Then I need to multiply by z here, and then take the derivative again. That will give me lambda tau square e lambda tau c minus 1 z. This is what I'm taking this derivative first, and then let me take derivative of this guy. I get lambda tau e lambda tau c minus 1. Now I'm going to set c equal to 1 here. That will give me lambda tau. This term I get lambda tau here, and this term here I get lambda tau square here. Okay, that's the second moment. Second moment is just lambda tau square plus lambda tau. So therefore, like the variance of this n here will be just equal to the expectation the second moment minus the mean square, that's equal to lambda tau square plus lambda tau minus lambda tau square, that is equal to just lambda tau. So actually the variance is the same as the mean, is just equal to lambda tau in this case. So again, we can use the similar trick to find the higher moment here. So to summarize what we did, like for our discussion on Poisson process, basically, as I mentioned, it's very important just to remember the picture of the Poisson process is we are going to consider if we have a small interval, and in the interval, the arriving, whether there's a packet arrive or not, will be independent of all the other intervals, like all the other times, and also like this in this interval here, or like in all the other intervals, also the weight of arrival, or like the probability that there will be arrival, will be stationary or not changing. And using just this picture, we are able to derive the inter-arrival time that will have a distribution. It's just a exponential distribution, lambda e to the minus lambda t, and this is the inter-arrival time, and the distribution of number of packets in the system, number packet, or also I should say number of arrival. I'm sorry, I mean number of arrivals within tau will be used Pn here. The Pn m, let's say, is just equal to this exponential lambda tau to the m over m factorial. And for the mean of this guy will be just equal to inter-arrival time will be just okay, let mean and variance. Mean is just equal to 1 over lambda, and variance is just equal to 1 over lambda square. And for the number of arrival will be just lambda tau, and this will be lambda tau also. Okay, let's consider a numerical example, a very simple numerical example. Let's say the arrival rate is 5 arrivals per second. You can think of this arrival as customers or packets or so on. Or maybe packets is more realistic if we have 5 arrivals per second. And then like, let's just consider 1 second period. And within this 1 second period, we want to ask, what's the probability that like we have more than 2 arrivals, let's say. With all these probabilities here, it should be very easy to find this probability, to solve this problem here. The probability that we have more than 2 arrivals, okay, that will be the probability that excluding the case that we have 1 arrival or 0 arrival, right? So therefore will be simply equal to 1 minus the probability that the number of arrival will be less than or equal to 1, or more explicitly, it's just 1 minus probability to have 0 arrival and probability of 1 arrival. We can just use this equation here. Probability of 0 arrival is just e to the minus 5 as lambda tau is equal to 5. with 5 to the 0 over 0 factorial, and probability 1 arrival is e to the minus 5 to the power 1 over 1 factorial, and that is just 1 minus 6 e to the minus 5. And that's just a very simple example.